So, we have learned so far that what is the physics behind different coordinate systems in space-times, what is the physics behind curvilinear coordinates, what is the physics behind curved space-time, etc., etc. And finally, we have obtained Einstein equations from Einstein-Hilbert action. And starting with this lecture, we're going to work with the solutions. We're going to describe solutions of the Einstein equations. In this lecture, we're going to start with the simplest exact solution of, which is spherically symmetric Schwarzschild solution of the Einstein equations. So that solution appears to be, it solves the Einstein equations in the case when a cosmological constant is set to 0 and there is no matter. Energy momentum tensor of matter is also 0. So as we have explained during the previous lecture, we have to solve this equation. So this is the equation we're going to address right now. And now we're going to find non-flat space solution of these equations. Namely, we want to consider spherically symmetric solution. And to consider spherically symmetric solution, it is better, instead of using Cartesian coordinates, which are t, x, y, z, it is convenient to use spherical coordinates in spatial path. So we're going to use this coordinates, t, r, theta, and phi. So these are the seminal spherical coordinates in three-dimensional space. So the most general metric which respects spherical symmetry has the following form. ds squared is equal to gtt, which is a function of only r and t, dt squared, plus 2gtr, which is a function of r and t also, dt, dr, plus g r r, which is again the function of r and t only, dr squared, plus k, which is a function of r and t only again, times d omega squared. What is d omega? D omega squared is a metric, well-known metric on the unit sphere, which looks in spherical coordinates, looks like this. So this is a metric on the unit sphere. The range of validity of r is from 0 to plus infinity. So it ranges from 0. So this is the radii. The range of validity of phi is, as usual, from 0 to 2 pi. And the range of validity of theta is from 0 to pi. This is important. And why this metric respects spherical symmetry? Well, let's consider its time slice, meaning that t constant slice. It means that dt is 0. When dt is 0, this drops off, because dt is 0. What remains is this thing, and this is the metric, this is a spatial part of the metric, so this plus this is a spatial part of the metric. And this spatial part of the metric for t constant is sliced as onion by spheres whose radii are fixed by this quantity. So this part of the metric specifies the radii, because it specifies the distances in r, proper distances in r direction. And this part specifies the area, how the area of the spheres is changing. We encounter a little bit unusual for the first time situation that our space is sliced as onion with spheres for a given moment of time. The radii of these spheres are set by this quantity, while the areas of these spheres are set by this quantity. And these two quantities are not related to each other. So it is not that we have a sphere of radius r and its area then is 4 pi r squared. This is not the relation we encounter here. So the radius is set by this quantity, the area is by this. This is somewhat unusual, but otherwise... Anyway, that's the reason we consider this as a spherically symmetric situation. Of course, if one chooses a different reference system, one can lose this symmetry, this explicit form. But for us, it's important that there is a reference system in which metric looks like this. And this metric is invariant under the remnant two-dimensional transformation. So if we choose only this part, this metric is invariant under the coordinate transformations if one takes a vector xa, which is t and r, which has components like this. So a runs from 1 to 2. So this metric is invariant under the following transformation. So if one chooses g bar ab as a function of x bar, it is g cd function of x dxc dx bar a dx d dx bar b. And at the same time, we can also transform this one. This one transforms as a scalar. So k bar of x bar is nothing but k of the function of x, which is in its own right is a function of x bar. So under such transformations, this part of the metric transforms as a two-dimensional tensor with two indices, and this part of the metric transforms as a scalar. So we have two functions. So basically we have two functions, r bar as a function of tr and t bar as a function of t and r. So we have two functions. These two functions can be used via this transformation to fix two out of these four independent. So we have 1, 2, 3, 4 functions. So using these two functions, we can fix two out of the four. And the convenient choice for future is to put GTR. So GTR to 0. So which means that we fix this to be 0. And K as a function of RT to be equal to minus R squared. Minus R squared. So this will be, then the spheres will have this area, but the radius of the sphere can be different from R due to this presence of this term. So after renaming the components into more standard form, if we name GTT as exponent of the function nu, which is function of, and GRR as minus lambda TR, then we arrive at the following expression, ds squared equals to nu RT dt squared minus exponent of lambda RT dr squared minus r squared d omega squared. So this is a metric we are going to work with in the following. But let us stress that this metric is still invariant under the remaining transformation, so we can change t to the t bar, which is a function of original t, so we can change this coordinate. simultaneously, but this, I mean, we want to respect spherical symmetry, so we don't want to touch this part of the metric. That's the reason we transform only time. So if we change this, this part is changed, but then we can shift this part as follows. So nu bar as a function of r and t bar, r and t bar, is just original nu as a function of r t of t bar plus log dt dt bar squared, and lambda transforms as a scalar. Lambda transforms similarly to this. So what we did so far, we want to find a spherically symmetric solution of these equations. Spherical symmetry up to some redefinitions, change of coordinate transformation. So generic spherically symmetric metric can be represented in this form. That's our point so far. Now we're going to calculate for this metric components of Ricci tensor and put them to 0. That's what we're going to do right now.